Next example of linear combination. In R3, if S is set E1, E2, E3. What is E1? E1 is 1, 0, 0. E2 is 0, 1, 0. And this is 0, 0, 1. E3 is. This is the subset of R3. S is subset of R3. Then any XYZ, any element of this R cube, for all XYZ belongs to R cube. That is, any element of R cube is of this type, XYZ or ABC. It expressed in the form x into E1. X into E1 means x into 1, 0, 0 plus y into 0, 1, 0 and z into 0, 0, 1. So we can express this XYZ very simply, that the coefficient values of K1, K2, K3 are what? X, Y and Z. So if you can apply the previous procedure, that is we write this XYZ as K1 1, 0, 0 plus K2 0, 1, 0 plus K3 0, 0, 1. And if you apply the method of scalar multiplication, definition of scalar multiplication and addition, then we have that x K1 is x, K2 is y and K3 is z. Okay, so we can express any element. For example, suppose 1, 2, 3 is the element. Suppose 2, 3, 2, 3, 4 is the element of R3. 2, 3, 4. Then how we can write 2, 3, 4 as 2 into E1 means 2 into 1, 0, 0 plus 3 into 0, 1, 0 plus 4 into 0, 0, 1. So we can express any element of R cube as a linear combination of these three vectors, E1, E2, E3. So what is the set of all linear combination? Is called a linear span of set S. So this is the next definition actually, linear span. So you note this thing, that from this example, every vector of R cube is expressed as a linear combination of these three vectors, every vector. So in the previous example, in the previous lecture, we have seen that one vector is a linear combination of that three vectors of R3. But one vector, that the same vector 1, 2, 3 is not linear combination of the remaining vectors in the previous example. So but these are the three vectors are in such a way that every vector of R3 is a linear combination of these three vectors. Every vector, we take any vector, then it can be expressed as a linear combination of these three vectors. That is, if you take the element x, y, z, then it is x into E1 plus y into E2 plus z into E3. So these are the three elements, and in therefore LS is equal to R3. What is LS? LS is set of all linear combination of these three vectors. Set of all types of linear combination of these three vectors. For example, one of the linear combination of these three vectors is what? 2 into this plus 3 into this plus 4 into this E3. So it is equal to what? After applying the definition of addition and multiplication, scalar multiplication, we have it is equal to 2, 3, 4, the 3 tuple 2, 3, 4. So we have every element of R3 as a linear combination of these three vectors. Means LS. What is LS? LS is the set of all linear combination of V1, V2, Vn. What is S is suppose V1, V2, Vn. Then what is LS? LS is the set of all linear combination, all possible linear combination of V1, V2, Vn. So what are the linear combination of E1, E2, E3? Each element of R3 is a linear combination of these three vectors, and so we have the what is the set LS now? LS is the set which contains every element of R3, because every element of R3 is expressed as a linear combination of these three vectors. And what is definition of LS? LS is the set of all possible linear combination of E1, E2, E3, because S is E1, E2, E3. So the set LS is what? Set LS is called linear span of set S, and is what? Is the set of all linear combination of E1, E2, E3 elements of S. So what is LS? Therefore it is equal to R3, because every element of R3 is expressed as a linear combination of these three vectors. And so what is LS? LS is the set of all linear combination of E1, E2, E3. Means every element S contains every vector of R3, means LS is equal to R3. Okay, so if LS is equal to R3, in such a way, in such a case that we say R3 is spanned by S, or S spans R3. So in the next definition, we will see this, that if LS is equal to R3, then we say S spans R3. Okay. So next problem is the polynomials 1x, x square, x raised to n spans Pn. That is, every vector of Pn is a linear combination of these three vectors. Every vector. Since every polynomial in Pn or every element of Pn is written as a linear combination of these three vectors, these n vectors. What are that? N plus 1 vector. These are n plus 1 in number. So if you take any polynomial Pn, then it can be expressed as a0 plus a1x plus a2x square plus an x raised to n. What is Pn? Pn is the vector space of all polynomials of degree less than or equal to n with real coefficient in x. Okay. So what is Pn? Pn is the set of all polynomials in x of degree less than or equal to n. So every vector of Pn or every element of Pn is written as a linear combination of these n plus 1 vectors. How we can write the linear combination? A0 plus a1x plus a2x square plus an x raised to n. A0 into 1 plus a1 into x plus a2 into x square plus in this way an x raised to n. So every element of this Pn is written as a linear combination of these n plus 1 vectors, and therefore this set, the set of all these n plus 1 vectors spans Pn. That is, if we write the set S as 1 comma x square comma xn, then Ls is equal to Pn. Okay. So this set, this polynomial, the polynomial, these n plus 1 polynomials or elements spans Pn, or we can say every vector of Pn expressed as a linear combination of these n plus 1 vectors. How can we write any vector of Pn is written as this: a0 plus a1x plus a2x square plus an x raised to n. So every element of Pn is a linear combination of these vectors, and therefore these vectors span Pn. So in the next example, express q is equal to 2 plus 6x square as a linear combination of P1, P2, P3. So the same procedure, we have to express the one vector as a linear combination of remaining three vectors. So take three scalars. So let k1, k2, k3 be scalars such that q is equal to k1 p1 plus k2 p2 plus k3 p3. Same procedure, we have to express the one vector as a linear combination of the three vectors. Suppose this is u bar, and we have to express it is equal to v1 bar plus v2 bar plus v3 bar. Then take three scalars k1, k2, k3 like that. U bar is equal to k1 v1 plus k2 v2 plus k3 v3. Like same procedure of R3 is here. That is, we have to express this q as a linear combination of p1, p2, p3, and therefore take k1, k2, k3 scalars be scalars such that q is equal to k1 p1 plus k2 p2 plus k3 p3. And now we have to find the values of k1, k2, k3. If these values exist, then we say that q is a linear combination of p1, p2, p3. And if this k1, k2, k3 does not exist, then we say this q is not linear combination of these p1, p2, p3. So 2 plus 6x square, the value of this q. Then k1, this write p1, write p2, and write p3. All these q, p1, p2, and p3 are the elements of p2. What is p2? P2 is the vector space of all polynomials of degree less than or equal to n with real coefficients. Okay. So P2, these are the elements of all these are the elements of P2. Set of all polynomials of degree less than or equal to 2. So substitute the value of q, p1, p2, p3, and then multiply by k, multiply k1, k2, k3, and simplify. That is to collect the constant coefficients. What are that? 2k1 plus k2 plus 3k3. Then coefficient of x are what? k1 minus k2 plus 2k3 x. Then coefficient of x square are what? 4k1 plus 3k2 plus 5k3 x square. Okay. Then compare the coefficients of LHS and RHS. The constant coefficient in RHS is 2k1 plus k2 plus 3k3, and in LHS it is equal to 2. Then the coefficient of x in RHS is k1 minus k2 plus 2k3, and the coefficient in RHS in LHS of x is 0. There is no term x. So its coefficient is 0, so is equal to 0, and the coefficient of x square is this, and in LHS it is equal to 6. So we have the three equations and three unknowns. Now we have to solve this system, and we have to find the values of K1, K2, K3. So apply the Gauss elimination method, or by using calculator, we can directly obtain the answer of K1, K2, K3. So what is the answer? K1 is 4, K2 is 0, and K3 is -2. So how we can solve this system by Gauss elimination method? That is form the augmented matrix, and then augmented matrix means the matrix of coefficient with the matrix B, AB, matrix AB, and then convert the matrix to, reduce the matrix to echelon form, and then write rank of A and rank of AB. Note that rank of A and rank of AB are equal, and therefore the given system is consistent. And then after rewriting the equation, we have the values of K1, K2, K3 as 4, 0, and -2. And then substitute these values at this place. So we have Q is equal to 4P1 plus 0P2 minus 2P3. And this is what? This is the Q as a linear combination of P1, P2, P3. So Q expressed as a linear combination of P1, P2, P3. The coefficient are 4, 0, and -2. So write the vector U as 1, -2, 5 as a linear combination of these three vectors. So again, take three scalars K1, K2, K3, B scalars such that U bar is equal to U bar, or U is equal to K1 V1 plus K2 V2 plus K3 V3, and substitute the values of U bar, U V1 V2 V3. Okay, so we have this after application of after multiplying by applying the definition of scalar multiplication, we have this, and after applying the definition of addition, we have this, that is the addition of corresponding elements. So these are the element of R3. All these U, V1, V2, V3 are the element of R raised to 3, the vector space of three tuples. And what is the addition and scalar multiplication in that vector space? Usual addition and usual scalar multiplication. So we have this by equating, then equating the LHS and RHS, we have K1 plus K2 plus 2K3 is 1, then K1 plus 2K2 minus K3 is -2, and similarly this is equal to 5. So this is the system having three equations and three unknowns. We have to solve the system by using Gauss elimination method, or by using calculator we can find the direct answer. But if the system is inconsistent, then calculator use is not the proper use. The calculator, when we can use calculator, if the answer is integer, the answer of K1, K2, K3 is integer. So don't use calculator everywhere. Somewhere we have to write the augmented matrix, and we have to reduce it to echelon form. So write the augmented matrix. This is the augmented matrix, the combination of A, this is A matrix, and this is the B matrix. So write here this line, or don't write this line. So this is A. A means the matrix of coefficient 1, 1, 2, then 1, 2, -1, 1, 3, 1, and then 1, -2, -2, 5 is the matrix of constant. So this is the augmented matrix AB. We have to reduce this matrix to echelon form. So here is 1. So we have to reduce these two elements as 0. So the operation are R2 minus R1, R3 minus R1. We have 0, 0 at this place, and we have the, so R2 minus 2, 1 minus 1 is 1, 1 minus 1 minus 2 is -3, -2 minus 1 is -3, then 1 minus 1 is 0, 3 minus 1 is 2, then 1 minus 2 is -1, and 5 minus 1 is 4. Then we have to reduce this element. This is 1. So we have to reduce this 2 as to 0. So for that, R3 minus 2 R2 by using 1. By using second round, we have to reduce this element to 0. So we have 0, and this -6 plus 6 minus 1 is 5, and then plus 6 plus 4 is 10. Okay. So then we have to reduce this 5 to 1. So take the operation 1 by 5 R3, or R3 by 5. 1 by 5 R3, 1 by 5 into R3. So we have 1 and here 2. And this is an echelon form. This is matrix is in echelon form. Why this matrix is in echelon form? Because it satisfies the three conditions. In every row, first non-zero element is 1 and is called leading one, and the leading one of lower row is to the right of leading one of upper row. And if there are 0 rows, then are at the bottom. So here is no 0 row. So this is an echelon form. So from this we write the rank of A. So this matrix is the echelon form of the matrix A. And how many non-zero rows in this matrix? 1. This is also non-zero, and this is also non-zero. Okay, so up to this line, this is the echelon form of the matrix A, and from it we say that the rank of A is 3, because what is the rank? Definition of rank of matrix: rank of matrix is number of non-zero rows in its echelon form. So this is the echelon form of the matrix A, and it contains 3 non-zero rows, and so rank of A is 3. And this whole matrix is the echelon form of the matrix AB, and it also contains 3 non-zero rows. So rank of AB is also 3, and so rank of A is equal to 3, and rank of AB is equal to 3, and therefore rank of A is equal to rank of AB, and therefore this system is consistent. And so how we can write the find the solution? Rewrite the equation. So first equation is K1 plus K2 plus 2K2 2K3 is equal to 1. The second equation is K2 minus 3K3 is equal to minus 3, and the third equation is K3 is equal to 2. So substitute K3 is equal to 2 in upper equation, we get the value of K2, and then substitute K2 and K3 in the above equation, we have the value of K1. So K1 is 2, K3 is 3, and K2 is 3, and K3 is 2. And then we write this U bar 1 minus 2, 5 is equal to K1 as 2, 1, 1, 1 plus K2 as 3, 1, 2, 3, and K3 as 2, 2 minus 1, 3. So we have this is what? This expression is what? This is this A vector is a linear combination of these 3 vectors: 1, 1, 1, 1, 2, 3, and 2 minus 1, 1. And these are the scalars 2, 3, and 2. Okay, K1, K2, K3. So this is so what is the question? We have to express this U bar as a linear combination of these 3 vectors. So U bar expressed as a linear combination of V1, V2, V3. So determine whether the vector spans R3. These 3 vectors spans R3. So when these 3 vectors spans R3, if every vector of R3 expressed as a linear combination of these 3 vectors, when we say that these 3 vectors spans R3, if every vector of R3 expressed as a linear combination of these 3 vectors, so take any vector from R3 as ABC belongs to R3B arbitrary vector, and try to express this vector as a linear combination of V1, V2, V3. So if this vector expressed as a linear combination of these V1, V2, V3, then we say that every vector of R3 expressed as a linear combination of these 3 vectors, and then we say that this V1, V2, V3 span R3. So what is the span? This is the definition of spanning. Okay, set of all linear combinations of S, elements of S, is called linear span of set S. And if LS is equal to V, then we say that LS is equal to V, then we say that S span R3, S span V. When we say S span V, if LS is equal to V, and when LS is equal to V, if every vector of V is expressible as a linear combination of vectors in S. So we have to show here these 3 vectors. We have to determine whether these 3 vectors span R3. So when these 3 vectors span R3, if every vector of R3 is expressed as a linear combination of these 3 vectors. So take any vector as, suppose U bar ABC belongs to R3B, any vector from R3. Don't take particular vector like this. These are the particular vectors. That is, this 1 minus 2, 5 is the particular vector. So we have to take the general vector, any vector. Okay. So and apply the same procedure. 1 minus 2, 5 expressed as a linear combination of these 3 vectors. Same procedure. If we have the values of k1, k2, k3, then we say that this vector is a linear combination of these vectors. So we have to determine whether these three vectors spans R3. So when these three vectors span R3, if every vector of R3 is a linear combination of, is expressed as a linear combination of these three vectors. So ABC, as suppose U, ABC belongs to R3, be any vector. Let K1, K2, K3 be scalar such that ABC is equal to K1 2 1 0 plus K2 0 3 minus 4 plus K3 1 minus 1 2. So we apply the same procedure. We have to try to express this ABC as a linear combination of these three vectors. So apply the definition of scalar multiplication. So we have this. Then after applying the definition of vector addition of three vectors, we have this 2k1 plus 0 plus uh, k3. It is not 2k 3k3, just k3. Then k1 plus 2 plus 3k2 minus k3, the second. Then 0 minus 4k2 plus 2k3 minus 4k2 plus 2k3. Here write only k3, and then equating the coefficient, we have 2k1 plus k3 is equal to a. This is right now. Then k1 plus 3k2 minus k3 is equal to b, and minus 4k2 plus 2k3 is equal to c. Now we have to solve these three equations, this system, and we have to find the values of k1, k2, k3. If these values of k1, k2, k3 does not exist, that is, if this system is inconsistent, then we say that this vector is not linear combination of these three vectors. This ABC is not linear combination of these three vectors. And then we say that this three vector does not span R3. Okay, but if this vector, if this system is consistent, that is, if we have the values of k1, k2, k3, then we say that this ABC is expressed as a linear combination of these three vectors, and then we say that these three vectors spans R3. Now we have to solve this system by using the same method, Gauss elimination method. So prepare the augmented matrix. Augmented matrix is what? 2, the coefficient of k1 is 2, coefficient of k2 is 0, coefficient of k3 is 1. So 2 0 1, then 1 3 minus 1, and 0 minus 4 2, ABC. Okay, ABC is the matrix of constant. So this is the augmented matrix, combination of A and B, matrix capital A and capital B. So combination of the two matrix A and B, augmented matrix. Now we have to reduce this matrix to echelon form. So first reduce this 2 to 1. So interchange the rows first and second, R1 2, right? R2, this type notation, or R, capital R in bottom, R1 2. That is the interchange the first and second row. We have this. We have 1 at this place. Then we have to reduce this 2 element to 0. Already it is 0. So reduce this 2 to 0. So R2 minus 2R1 is the application. And then we have this 0. Then minus 6 and minus plus 2 plus 1 is 3. And then we have A minus 2B. A minus 2B by using this approach. And this last row as it is. Then we have to reduce this minus 6 to 0. 1 minus 6 to 1. So take 1 by a R2 by 3, or R2 by 3, or we take R2 by 6 application, or R2 by minus 6. Okay, so R2 by 6 gives this. Okay, and then we have to reduce this below element as 0. So if you multiply by plus 2, then minus 2, then we have plus 4 and minus 4 is 0. So R3 minus 2R2 is the application. So we have 0 0 at this place, at a time 0. So apply this procedure, or apply our usual procedure. So after this step, we have to reduce this minus 6 to 1. So apply minus 1 by 6, R2 as application, minus 1 by 6 R2. Then we have some matrix, and then reduce this element, below element to 0. So while reducing this element to 0, this element also becomes to 0. So this echelon, this is an echelon form. So it may be very student to student, this form, echelon form. This is not unique echelon form. This matrix format is depend on, this echelon form is depend on your calculation. So if we apply another row applications, row transformations, then we have another form of this echelon form. But every if we write the rank of A and rank of AB, then we observe that the rank of A and rank of AB are same of all of you. So here we have the rank of A as 2, because A contains only two non-zero rows up to this line. This is the echelon form of the matrix A, and this rank of A is 2 because there are two non-zero rows. This last row is 0. And if you consider whole matrix, this whole matrix, then it is an echelon form of the matrix AB, and it contains three non-zero rows. This is non-zero row, this is non-zero row, this is non-zero row. So, and therefore rank of AB is 3, and therefore the system is inconsistent, and therefore K1, K2, K3 does not exist, and therefore we say that ABC is not linear combination of these three vectors V1, V2, V3, and therefore every vector of R3 is not expressible as linear combination of V1, V2, V3, and therefore these three vectors does not span R3. So this is the answer. Our we can observe that if this element, this combination of ABC is 0, suppose this element is 0, the value of this equation, this quantity is 0, that is C minus 2A minus 2B divided by 3 is 0. Suppose if we adjust the CABC such that this is equal to 0, then in that case the system is consistent. But when this is equal to 0, this is C minus 2A minus 2B divided by 3 is not 0 for all ABC. It is equal to 0 but for some ABC. And that elements only expressed as a linear combination of V1, V2, V3, for which this is equal to 0. That element only for that ABC, we have that ABC as a linear combination of these three vectors. But it is not equal to this quantity, is not equal to 0 for every ABC, and therefore some elements of R3 may be expressed as a linear combination of V1, V2, V3, but all elements of R3, every element of R3 is not expressible as a linear combination of V1, V2, V3. So this shows that above system has no solution or infinitely solution. Infinitely means solution if this is equal to 0, which depends on ABC. And this means that every vector in R3 may not be linear combination of V1, V2, V3. Not every vector. Some vector of R3 may be expressed as a linear combination of V1, V2, V3, for which this quantity is 0. This quantity is 0 for that values of ABC, means for that vector ABC expressed as a linear combination of V1, V2, V3. So this system, the above system has no solution. In the case that rank of A is 2, rank of AB is 3, and therefore the above system has no solution, and therefore every vector, therefore ABC, this vector ABC is not linear combination of V1, V2, V3 for all ABC, and therefore we say that these V1, V2, V3 do not span R3. So if it is expressed as a linear combination, then we can say it is a span R3. So we will see the same type examples in the next lecture, that is a linear combination and spanning examples. Okay.